Hello. Welcome to the workshop. Today, we are talking about two very important things that make our modern world possible. I am talking about steel, my friends. Specifically, two types you hear about all the time: hardened steel and tool steel. They sound similar, no? Both are strong, both are tough. But are they the same thing? Not quite, boss. Think of it like this. All comedians are performers, but not all performers are comedians. Similarly, most tool steels are hardened, but not all hardened steels are tool steels. Understanding this small difference is super important. It is the key to making things that last. So, what exactly is tool steel? This is not your average steel used for making a simple gate or a chair. No, this is the VIP of the steel world. Tool steel is a special family of carbon and alloy steels. They are created with extra ingredients, like a master chef adding secret spices: chromium, vanadium, tungsten, molybdenum. These additions give the steel special powers: the power to be incredibly hard, the power to resist getting worn out, the power to keep its shape even when it gets very, very hot. D2O1, A2, M2. Now let's talk about hardened steel. This term is a bit more general. It is more of a description of what has been done to the steel. Hardened steel is any steel that has gone through a process to make it harder. Section 2. Hardness and strength. Explained, alright, let's get into the numbers. Numbers in steel tell you how it will behave. First big number, hardness. Hardness. Resistance to scratch or indentation, like a defensive shield. Measured on the Rockwell C scale, also called HRC. Test. A diamond cone pressed into steel. Deeper indentation. Lower HRC. Hardened tool steels have high HRC. Typical range, 55-66 HRC. You won't scratch this with car keys. Examples: time. D2 tool steel, about 60-62 HRC. M2 high-speed steel, about 62-66 HRC. M2 cuts fast without losing its edge. H13 hotwork steel, around 45-52 HRC. H13 is tough hot, not just hard cold. Higher HRC. Harder surface for cutting, but not everything. Next, tensile strength. Simple idea. How much pulling force before it snaps? Think tug of war with a steel rod. Tensile strength. The point where the rod breaks. Critical for safety and design. Tools and dies must handle expected stress. High-quality tool steels get impressive tensile strength. After heat treat, about 1,000 to over 2,000 megapascals. 2,000 MPa is like hanging 3 large cars from a 1-inch square bar. Tensile strength varies with grade and heat treatment. M2 sits at the higher end, very strong and rigid. H13 may have lower tensile strength at room temp, optimized for high heat. When designing, check tensile strength to avoid failure. It's the steel's muscle. Hardness. Surface property, but tensile strength, core strength. Both needed for the full picture. Section 3. Wear versus toughness. The great steel trade-off. Now we come to the most classic drama in the world of materials. It is a story of give and take. I am talking about wear resistance versus toughness. Wear resistance is a steel's ability to say no to abrasion, scratching, general surface damage. It is the quality that lets a knife stay sharp after cutting through 100 boxes. High hardness and special hard particles called carbides inside them, like the high carbon, high chromium, D2 steel, are the kings of wear resistance. They just refuse to get worn down. On the other side of this family feud is toughness. Toughness is not the same as strength or hardness. Toughness is the steel's ability to absorb energy and deform without fracturing. It is the quality that lets a hammer handle an impact without chipping or shattering. It is about being able to take a punch. If a steel is very, very hard, it often becomes brittle. Think of glass. Glass is very hard, but if you drop it, it shatters. It has zero toughness. In the steel world, a grade like A2 is famous for finding a beautiful balance. It has good wear resistance, but it is much tougher than D2. making it less likely to chip at the cutting edge. O1 steel is also known for being quite tough, even if it cannot match D2's wear resistance. So, how do you choose? It all comes down to how your tool is most likely to fail. Are your tools becoming dull very quickly but never breaking? This means they are wearing out. Your problem is low wear resistance. In this case, you should move to a steel with higher wear resistance, like D2 or even M2. You are sacrificing a little bit of toughness, but that is okay, because chipping was not your problem. You are solving the problem of wear. This is a common situation for tools that do a lot of slicing or cutting of abrasive materials. The edge just gets rounded over time. A more wear-resistant steel will hold that sharp edge for much longer. But what if the opposite is happening? What if your tools are staying sharp, but the edges are chipping, or the tool itself is cracking under shock loads? This is a failure of toughness. Your steel is too brittle for the job. In this situation, you need to move away from the ultra-high wear-resistant steels. You would choose a tougher steel like A2 or even a shock-resisting steel from the S series like S7. Steel on its own is like an actor without a script. It has potential, but it does not know what role to play. Heat treatment is the script. It is the director that tells the steel how to perform. This process is pure industrial magic, a kind of alchemy that changes the entire personality of the metal. The most basic step is called annealing. Heat the steel up and then let it cool down very slowly. Like sending the steel on a relaxing spa vacation. It relieves internal stress and makes the steel soft and easy to work with. Do this first so you can machine the steel without destroying cutting bits. Once shaped, it's time for the main event, hardening. The opposite of the spa day, intense, high-stakes action. Heat the steel to a specific very high temperature, over 800 degrees C. The crystal structure changes completely. Then at the right moment, cool it down extremely fast. This rapid cooling is called quenching. Quench in oil, quench in air, quench in water, quench in salts. Red-hot steel plunged into an oil tank, steam and smoke billowing. That shock freezes the high-temperature structure, making the steel incredibly hard. That's how you get a high HRC number. An unhardened tool is useless. A hardened tool is a superhero. But after quenching, the steel is super hard and very brittle, like glass. It is full of internal stress and would shatter under use. So we need another step, tempering. A cool-down session after a heavy workout. Gently reheat to 200, 500 degrees C and hold. This relieves stress and gives back toughness. Higher tempering. More toughness, but less hardness. It's a delicate balancing act, beyond basics. Other tricks exist. Case hardening. Harden the outer surface only. Surface wears resistant. Core remains tough. Perfect for gears. Cryogenic treatment. Freeze to 185 degrees with liquid nitrogen. Converts leftover soft bits to hard ones, boosting wear resistance and life. Heat treatment is not just a step. It is the science and art that unlocks a steel's true power. Now for the fun part. Let's talk about making things that cut. Choosing the right steel for a cutting tool is everything. It depends on what you are cutting, how fast you're cutting, whether you're hitting it or slicing it. Start with the workhorses. End mills drills. They spin very fast and get very hot. You need steel that takes heat and stays hard. Undisputed champion, high-speed steel. HSS, especially M2 grade. M2 was designed for this and keeps its edge even when glowing red. For heavier duty, consider solid carbide. M2 remains the reliable, general-purpose choice. Slicing and shearing at room temp. Giant sheet-cutting blades stamping punches. Heat is lower, wear is massive. D2 tool steel is popular here. High carbon and high chromium give it great wear resistance. A D2 die can stamp hundreds of thousands of parts, but D2 can be brittle and may chip under shock. If chipping is a risk, use A2. A2 gives better balance, wear resistance with more toughness. Simpler shop tools, hand taps, basic lathe tools. Priority, toughness and cost over speed. O1 is ideal, an oil hardening tool steel. Oil hardening is more forgiving than air hardening like A2 and D2. 01. Good hardness, excellent toughness, lower cost. Less durable than D2, but less likely to chip and cheaper to replace. When the work is hot, forging red-hot steel hot extrusion, tools face extreme heat and repeated impact. D2 or M2 would soften and deform. Use hot work steels. H13 is the king. H13 keeps hardness and toughness at high temps and resists thermal shock. For tools touching red-hot metal, H13 is almost always the answer. Cutting tools are only one part of the story. Steels are also used to shape and form other materials in processes that use molds and dies. Let's first look at molds for plastic injection. When you create a plastic part, you inject molten plastic under high pressure into a steel mold cavity. These molds need good wear resistance for thousands of cycles, and they must be polished to a mirror finish to leave a smooth surface on the plastic. For many general-purpose molds, a pre-hardened steel like P20 is very common. It arrives moderately hardened from the supplier, so the mold maker can machine the cavity and use it without complex heat treatment. But if you're making millions of parts, or using abrasive plastics like glass-filled nylon, you need something tougher and more wear-resistant. Enter H13 Tool Steel. It's a hot work steel with excellent toughness, good wear resistance, and the ability to be polished to a high shine, making it a top choice for high-volume, high-performance injection molds. It can handle pressure and abrasive plastic flow for a very long time. For optical quality parts, specialty stainless mold steels are used because they can be polished even higher than H13. Now shift to molten metal. Die casting forces molten aluminum, molten zinc, molten magnesium into a steel die. This is a brutal environment. The die faces extreme temperatures, high pressures, and constant thermal shock, cycling between hot fills and cooling lubricant sprays. H13 is the only steel that reliably survives this. It maintains strength and resists cracking at high temperature. Other steels would soften, erode, or crack quickly. For die casting, H13 is the industry standard. Finally, progressive dies for stamping sheet metal. A strip of metal moves through a series of stations that bend, punch, and form it into a finished part. These dies need mixed properties. Cutting sections need high wear resistance, often D2. Bending and forming sections need more toughness, often A2. Large progressive dies are assemblies of different tool steels, each chosen for its station. So, after all this talk, let's wrap it up with some clear recommendations. The big story is the constant battle between wear resistance and toughness. The harder and more wear-resistant a steel is, the more likely it is to be brittle. The tougher a steel resists chipping and resists cracking, but it will likely get dull faster. Your job is to be the referee and pick the winner. Diagnose how your tools are failing. If the edge is getting dull but not breaking, you need more wear resistance. If the edge is chipping, if the tool is cracking, you need more toughness. Let's make this super simple. Here are your go-to picks. For high-speed cutting, drills for high-speed cutting, end mills, where the tool gets hot, your champion is M2 high-speed steel. For long-life dies, for shear blades, cutting abrasive materials at room temp. When wear is your main enemy, your hero is D2. If those D2 tools start chipping because of shock, because of impact, bring in the balanced fighter A2. A2 gives decent wear resistance and much better toughness. For jobs with red-hot metal, like forging, like die casting, there is only one real choice: H13. H13 is the undisputed king of the heat. For simple, cost-effective general workshop tools, punches, drifts, basic machine tooling, 01 is a fantastic, reliable option. 01 is tough, easy to heat treat, and gets the job done. There is no single best steel.